Hi. It's a common doubt that sometimes when we are doing the heating and the cooling load calculation using HAP software, the airflow rate or dehumidified airflow rate might be high. Normally, for comfort air conditioning system, the equipments that we are purchasing from the market, most of the manufacturers know, they'll be keeping for each ton of refrigeration nearly 400 CFM of airflow rate, comfort air conditioning system. As a rule of thumb, we are also following in the market 1 ton of refrigeration cooling load in comfort air conditioning system, nearly 400 cubic feet per minute CFM of airflow rate can come. But this is a rule of thumb rule. It is not correct always, because with respect, airflow rate within the space when we are doing the heating and the cooling load calculation is affected by various other factors as well. So this 1 ton 400 CFM might not be always accurate. It may vary. Correct. This 1 ton of refrigeration 400 CFM is normally for 24 degrees Celsius dry bulb temperature and 50% relative humidity comfort air conditioning system. Most of the time that might be satisfying. It doesn't mean that always we need the same value. Sometimes per ton the CFM requirement might be more can come. Okay. And so, for example, how the softwares are doing the calculation for airflow rate, the simple calculation is only this. Sensible heat is equal to M into Cp into delta T. Correct. And latent heat, the room, when we are doing the heating and the cooling load calculation, you will be getting the total coil load. The total coil load is the summation of sensible coil load and the latent coil load. Correct. So airflow rate we can calculate by the help of sensible coil load, or we can calculate by the help of latent coil load as well. Equation may vary, so we can discuss this one, sensible coil load. That's why the room sensible heat remains always constant. What is a room airflow rate? See, when we are doing the heating and the cooling load calculation, you will be getting, let's say, let me generate a report. Okay, so I did a heating and the cooling load calculation of a space. I did, okay, I completed that using HAP, and the total coil load I'm getting 12.2 kilowatt. Okay, and the sensible coil load is 10.6 kilowatt. We are having 3 airflow rate, coil liter per second at this maximum block, sum of peaks on which one we have to select. Maximum block liter per second will be always good. Actually, if when you are generating a single zone building or only one space report, if you are generating, this one you have to select, means coil liter per second at June 17. June 17 is the peak time. So when the internal and external conditions are peak, we need 754 liter per second inside. But if it is a multi-zone building, in a per year, including diversity for all the space or the zone airflow rate when you are adding, you will be getting this maximum block liter per second. So multiple zone machine selection, you can select a maximum block liter per second only. Sum of peak peak zone liter per second is simply nothing. Without considering any diversity, the peak airflow rate the software will be adding together that you will be getting here. But we are not selecting the third value, means sum of peaks on liter per second for machine selection, because sometimes that might be slightly oversizing. That's why always the maximum block liter per second will be safe for multi-zone building. Whether single zone building, all the 3 values you will be getting same only. Okay. Anyhow, what exactly this one? This is called, sometimes we can call this as dehumidified airflow rate. Means this is simply nothing. Suppose if you are having a cooling coil, this cooling coil is able to extract 12.2 kilowatt of coil load. Okay, so to extract 12.2 kilowatt of coil load, how much amount of air has to be circulated through the cooling coil? That is this one, since it is a cooling calculation. Okay, but in case of cooling and a dehumidification process, the coil only will be doing it, right? Because the coil surface temperature we will be keeping less than the dew point temperature of room condition. So that's why when the air with the moisture is touching the cooling coil, the condensation or the latent heat removal will happen, right? So that's why sometimes this airflow rate, we used to call that as dehumidified airflow rate only, because when this amount of airflow rate is circulating through the cooling coil, the condensation is also happening. That's why. Fine. So this is simply nothing. This amount of air has to be circulated through the cooling coil to extract 12.2 kilowatt of or kilojoules per second of heat from your space. Simple, right? So this value, what all factors it will? Anyhow, room sensible heat. For example, sometimes this M from this equation, QS is the room sensible coil load in kilowatt. M is airflow rate in kilogram per second. We can convert that into liter per second as well. Anyhow, CP is specific heat of air only. It's a constant value, 1.005 kilojoule per kilogram Kelvin. Anyhow, room sensible load will be constant only because it is the amount of heat that is circulating within the space, the amount of heat that is transferred to the space through wall, floor, window, door, people, light fitting. That is constant. The airflow rate is not having any role in it. That is separate. So that's why room sensible load will be constant. Specific heat also constant. Then why this value is increasing? That's why delta T. What is delta T? What is this delta T? Delta T, for example, if you are having a cooling coil and your room set point is 24 degrees Celsius. Let's say a room I have set with the 24 degrees Celsius. And the temperature of air that is leaving from the cooling coil, that is called supply temperature. Supply temperature. So the difference between the room set point and the supply temperature, that is this delta T. Okay. So that's why if the supply temperature is increasing or decreasing, if the room set point is increasing or decreasing, that will be affecting this one. Which one? The airflow rate. We can check. For example, I'm having a space. Okay, let me close this one. This is space only. All the space input I have already provided. This we have already discussed in the HAP session. Okay, I'm just going to this one. And I'm just going to the zone component. Okay, under thermostat, you can see the set point is 24 degrees Celsius only. Set point, room set point is 24. If you're coming to the system component, central cooling coil, the supply temperature is now 12 degrees. Actually, HAP will be preset with a 14.4. You can check it, 14.4. Click OK. And let me generate. Right click, print and view design result, preview. How much airflow rate I am getting. Now my coil load is, because if the room set point is 24 degrees Celsius, okay, supply temperature, design supply temperature of 14.4 degrees Celsius. Okay, so 14.4 minus 24, actually this is a theoretical, but in actual case, the leaving dry bulb is 15.2, means coil leaving dry bulb is 15.2 degrees Celsius. A room set point is 24. So from that equation, as I told, Q is equal to M into Cp into delta T, correct? This is constant, this is constant. This delta T in this case will be 24 minus 15.2 only. 15.2. Okay, so in this case, I'll be getting the airflow rate of how much? 943 liter per second. This value sometimes will be higher only. Correct. This might be higher. So how much I'm getting now? For example, this is 12 kilowatt. 12 kilowatt is how much ton of refrigeration. We can change the unit in HAP itself. Otherwise, we can calculate like a 12 divided by, okay, 3.516. How much it is? 3.41 ton of refrigeration. 3.41 ton of refrigeration, 943 liter per second. So 943, I'm converting that into CFM, 943 into 2.119, correct. 1998, 1998. Okay, so how much this value divided by 3.41, this value divided by 3.41, how much CFM I am getting? 585 CFM I am getting. 585 CFM I am getting for 1 ton of refrigeration. So here it is not matching. Now 1 ton of refrigeration, we have normally as a thumb rule, we are getting 400 CFM, but here I am getting 585 CFM for per ton. Why it is? That is due to the sensible load only, because a room sensible load might be high. Room set point will be high. Supply temperature, how I can decrease this one? Okay, now I have to decrease this M. Sensible load, okay, anyhow, room that is generating is almost same old. Slight fluctuation will come. Cp is constant, delta T is increasing. If delta T is increasing, now the supply temperature is 14.4 only. Okay, I need to decrease the mass flow rate from 580, like this one, no? 1998 CFM or 985 liter, 943 liter per second. I need to decrease. How I can decrease? The first one, either if you are decreasing the sensible load, that is possible. Cp is constant, not possible. Sensible load, anyhow, the heat that is sensible heat that is generating inside the space, we can't decrease it. Safety factor we can adjust. Okay, anyhow, I will explain that. Sensible heat is decreasing, that may happen. Otherwise, delta T. Now the supply temperature is 14.4 only. If the supply temperature means is decreasing instead of 14.4, if you are selecting the supply temperature is 12, then theoretical supply temperature is 12, a room set point is 24, so 24 minus 12, the delta T will increase there, no? Then this value will decrease. We can try that is possible or not. Let me check it. I'm closing this one, okay? And I'm just going there, okay? I'm just going to the system component, central cooling. Now the supply temperature was 14.4. I am decreasing that into 12. Remember, see, for comfort air conditioning system, for cooling application, supply temperature will be 12 degrees Celsius to 15 degrees Celsius only. That will be between 53 degrees Celsius Fahrenheit to 59 degrees Celsius, degree Fahrenheit. So this is in imperial standard, this is in metric. Most of the cases, that is the normal range. But sometimes it can go below that, but it should be most of the coil, it should be higher than 10. This is the supply temperature. Like for heating also, heating cycle, supply temperature can be like a 35 degrees Celsius to 53 degrees Celsius can come. Means 95 degree Fahrenheit to 122 degree Fahrenheit, on that ranges, heating supply temperature also can vary. Okay, just for your knowledge I told. Anyhow, here I have decreased the supply temperature from 14.4 degrees Celsius to 12 degrees Celsius. Now click OK, check the report once again. Right click, print and view design result, preview. Now instead of 943, I'm getting how much? 754 liter per second only. How much CFM it is? 754, okay, into 2.119. 1597 CFM for 754 liter per second. Now per ton, how much I can get? Coil load slightly will vary. Before it was 12 only, now it is 12.2. That will come because when the ADP, everything is changing. Slight with respect to the room sensible heat ratio and all, slight changes can come. Even though not that much changes, before it was 12, now it is 12.2. Okay, anyhow, 3.41 ton, no? So 1597, now 1000 divided by the ton of refrigeration, how much? 3.41. Per ton, here I'm getting how much? Before it was 585 CFM per ton of refrigeration. Now I am getting 468 CFM per ton of refrigeration. Why it has happened? So that's why airflow rate is increasing. By adjusting the supply temperature, we can decrease it. The supply temperature, if you are increasing accordingly, this value will increase. Okay, that is one option. Any other option? Yes. See, even if I am keeping the supply temperature, even if I am keeping the supply temperature 14.4, I can decrease. Sometimes, no. In GCC and all, when you are working, the client might be saying that I need 19 degrees Celsius inside the room. I need 20 degrees Celsius inside the room. you might be keeping 14.4 preset temperature in the HAP. But if you are going to the thermostat, this value, cooling set point, since the client requirement is 21 or 90, you might be designing with that. For example, as per my client requirement, I need to design this for 21. Okay, so heating set point, I'll be adjusting into 19. Okay, fine, everything is, this one is, okay, you can go to the system component, central cooling coil, supply temperature is 14.4. Okay, when it was 14.4, what was the airflow rate? 943 liter per second, correct. But the set point was 24. Now, the supply temperature is same only. Room set point I am decreasing from 24 to 21. Definitely delta T, what will happen? Delta T will decrease. If the delta T is decreasing, means the difference between the supply temperature and the room set point is decreasing now. Mass flow rate will increase. Instead of 943, this value will again increase now. It can go up to 1000. Okay, let me check it. Click OK. Right click, print and view design result, preview. Now instead of the same load, 12.6, slight fluctuation will come due to the ADP changes and all. Now you can see, instead of 24 degrees Celsius, the room set point, when I am adjusting into 21 degrees Celsius, for the same design supply temperature of 14.4, the airflow rate has increased from 943 to 1462 liter per second. So it is clear that supply temperature is increasing or decreasing, airflow rate will get affected. Room set point. So most of the reason why the supply temperature is not matching with the manufacturer recommended 1 ton of refrigeration 400 CFM. This is a reason. This is a reason. Supply temperature might be the most of the cases reason. See, sensible coil load is a constant factor only. We can't decrease it. sensible coil load. But you can do one thing, even if your 24 degrees Celsius, this one you are keeping like a 24 degrees Celsius, we were getting like a nearly 943, correct, print and view design result. We were getting 943 liter per second, correct. But still, initial condition, still we can decrease it by adjusting the sensible load as well. But sensible load, you can't do anything. Rather, from the sizing data, safety factor of sensible load, if you are decreasing, means that is okay. Slight fluctuation can come in the airflow rate. Okay. Now, instead of airflow rate 943, we are getting 861. So that's why sensible coil load is increasing or decreasing, that can come. But you should not do that. Heat load that is generating is irrespective of internal and with respect to the internal and external conditions. So you should not adjust that. 15%, 10 to 15% safety factor is required. So don't do that. That's why simple thing. No? And what will happen if the required CFM we are not getting? Sorry. For example, after the heating and the cooling load calculation, we will be selecting the machine. When we are going to the machine selection, ton of refrigeration, airflow rate value, everything will be there. So normally plus or minus 10% fluctuation from the design value is permissible. Even if sometimes if you're not getting any option in the market, up to 20% is also, let's say you can close your eyes for time being at that time. But normally plus or minus 10 to 15% fluctuation from the design value is permissible. Sometimes ton of refrigeration might be matching, but airflow rate will not match. Because manufacturer availability per ton, it might be like a 400 CFM, but per ton we might be required 500 CFM. But coil load might be matching there. Means our designed coil load and the manufacturer coil load might be matching in that scenario, but airflow rate, the manufacturer machine, that might be less. What we can do, what might be the problem in it? See, for example, from the equation itself, we can see mCp delta T. Sensible coil load is constant, Cp is constant. For the same coil load, M is increasing. What about the delta T? Delta T will decrease. Means instead of our requirement, sometimes we might be selecting a machine with more flow rate, excess flow rate. But coil load is less. Okay. Coil load is less. Let's say when we are selecting an AC machine, coil load is less only, but airflow rate is more. What about if the airflow rate is increasing? What about the delta T? So if the airflow rate is beyond our requirement, if it is increasing, delta T will definitely decrease. Means the difference between the coil supply temperature, let's say that might be like T1, and the room temperature T2, this delta T means T2 minus T1, this value will decrease. Delta T, sorry, if the delta T is decreasing, can imagine a room we might have set with the 24 degrees Celsius. Okay. And let's say if supply temperature we have designed for 14 degrees Celsius. So 14 minus 24. So the delta T requirement will be 10 degrees Celsius. But sometimes instead of 10, so based on that only, okay, room temperature is 24. When this from the room, the hot return is entering, it might be like, let's say 24.5 degrees Celsius example, or let's say 25 degrees Celsius. Okay, this 25 degrees Celsius of air will be circulating through the cooling coil, the air temperature will decrease. Now, let's say instead of 10 degree, now we are having delta T got decreased. Now we are having a delta T of 7 degrees Celsius. So 24 minus 7, supply temperature might be decreasing into 17 degrees Celsius. Now this 17 degrees Celsius of air, a room hot air will mix together. Then we will be achieving that room set point of 24. Correct. Delta T is, this amount of airflow rate is increasing. Delta T will decrease. Supply temperature will get affected. If the supply temperature, for example, we have studied in the psychrometry classes for comfort air conditioning system, let's say 24 degrees Celsius a dry bulb temperature, in 50% relative humidity, the dew point temperature is somewhat near to 13 degrees Celsius only. In reality, when we are considering the room sensible heat ratio, bypass factor and all, this value will be slightly decreasing, or sometimes it can increase as well. Correct. Means you have to cool the air until this point, then only the effective condensation can come. But when the supplier temperature is much higher than 13 degrees Celsius, latent heat removal will not come properly. So that's why if the mass flow rate is increasing, delta T will decrease, supply temperature will increase, the air will not achieve the dew point temperature, so the effective condensation removal will not happen. Room relative humidity remains high in that scenario. That is a problem, main problem. Mass flow rate is decreasing, what will happen? Q is equal to M Cp delta T. M is decreasing, delta T will increase. Means room temperature is 24, okay? Our design value might be 14. Delta T is 10. But instead of 10, if the delta T is increasing into, let's say 14, what will happen? The mass flow rate is decreasing, delta T will increase. Okay, so then this 25 degrees Celsius of air will be entering, it will be cooling. Let's say since the delta T is 14 degrees Celsius, the supply temperature might be 10 degrees Celsius in that scenario. But as per our room requirement, the dew point temperature is somewhat near to 13 only, but excess cooling has happened there. That's why the surface temperature of cooling coil will be too less there. Since the dew point, the temperature of the air that is leaving from the cooling coil is much less than the dew point temperature of a room condition, excess condensation will happen there. Excess humidity removal will happen there. So the relative humidity in that room condition, no, that might be less than our requirement. Excess condensation can come. So these are the problems that is going to happen. Also, if the amount of airflow rate is too less, room cooling ACH can affect it, because normally for most of the comfort air conditioning system 14 to 16. But hospitals and all, as per ASHRAE 170, nearly 20 ACH has to be achieved for cooling. In that scenario, hospital cases and all, we are calculating the room airflow rate not as per the supply temperature or not as per the dispensable heat, as per the ACH only. So that we have discussed in the HAP session 1 or 2, I guess. But let's accept that hospital criteria. Most of the comfort air conditioning buildings, like we might be getting a room ACH of 14, 16 only. Means 1 hour, the entire room volume of air has to be circulated through the cooling coil. No, that is nearly 14 to 16. We have discussed already that in the HAP sessions. We are not repeating that again. This criteria, no, we need more time for that. Means a room ACH will be, we will not be getting the sufficient ACH for the complete. To recirculate means if the amount of air that we are circulating through the cooling coil is less, this room airflow rate is less, we need more time to circulate the room air through the cooling coil. So initial cooling time will be more. So the AC machine will be consuming more electricity. Your electrical consumption will be more there. And also uneven. For example, if the temperature, supply temperature is not proper, no, uneven stratification issue can come. No, air temperature will not be uniformly distributed everywhere. A lot of issue can come. So that's why plus or minus 10% differences from the load is fine for machine selection. And also when we are selecting the machine, whether medium speed, low speed or high speed selection has to be done. Always we have to select with the medium speed, but that also conditional only. Conditional. For example, I'm having a factory building. I'm designing a factory building, and I'm designing a library, and I'm designing a prayer room. Let's say office. I'm designing a factory, I'm designing an office, I'm designing a prayer room. Factory sound is not a concern. So that's why even if you are selecting, means like a high speed option, means if you are getting the selection on the high speed, that is fine. But even though factory will be also having the NC limit, correct? For example, if the NC limit of noise criteria limit means the sound that is created by the machine, that is called a noise criteria, and the noise NC value will be provided by the manufacturer. If the total NC value is less than, if the factory recommendation is 40 dB, if it is less than 40 dB, even if in the high speed, if you are getting that, you can select high speed also, no problem. But energy consumption will be very high, because high speed machine, the fan RPM will be blower motor RPM will be very high. That's why power consumption will be slightly high only there. Noisy. Noise issues can also come. But if the noise that is created by the machine, even if that is working at a high speed, that is within the limit of NC value, no problem. You can propose that. Prayer room and all. No. Normally for office building comfort air conditioning system, medium speed you have to select. That will be safe. Prayer room and all, the sound should be very less. Okay, so that's why low speed options you can select. But whether that is medium speed, high speed, or low speed, when the machine is working, if the noise criteria is within the limit, anything you can propose. But normally for most of the building, medium speed, we will be getting the right option. High speed and all, that might be bypass factor of the machine will be too high. Means amount of air that is touching the cooling coil will be less only. So that is not energy efficient in high speed, noisy, and uneven distribution of air within the space can come. These kind of issues are there. Okay, but wherever the sound is a concern, you can go for low speed selection. Wherever the sound is not a concern, you can go for high speed selection. Rest everywhere. Normally for comfort air conditioning system, hospital, hotel, library, residential application, medium speed, try to find a perfect option in the medium speed. But as you know, when we are selecting, let's say, let me check one technical data sheet provided by the manufacturer. So every technical data sheet provided by the manufacturer, you can find the NC value provided by the manufacturer. Now let me select it. Okay. Say this one. This is Daikin DX ductable unit. So in this you can see FDMR and 50 AV 1K. It's a machine. FDMR and 50 AV 1K. In the acoustics, we have already discussed how to select the sound attenuator, acoustic lining design and all. Okay, when it is working on medium speed, the effective overall dB is 45. Noise criteria overall will be 38. When it is working for low speed, it can come up to 35. When it is working for high, that will be 40. But if you are going to FDMR in 20, it will be working on low speed. The NC limit is 30 only. So as per our limit, we have to make sure that this noise limit is within the range, then we can propose. If it is not satisfying, then we have to go for sound attenuators. Then we have to propose additional acoustic lining. Accordingly, we have to match it. Okay, so this is a common concern. Normally, most of the students were asking what we have to do to adjust the airflow rate within HAP. So, but by adjusting the supply temperature, by adjusting the safety factor of sensible coil load, by adjusting this one, room set point, we can increase or decrease the airflow rate. But remember, 1 ton 400 CFM is a thumb rule. That might not be always correct. Because when the software or manually when we are calculating, as per the room sensible load only, or even latent load also we can use, the calculation might be different. So that's why with respect to the room load only, we will be calculating the airflow rate. That has to be satisfied when we are proposing the machine. If you are not finding the perfect match, we have to go for the different model. Accordingly, we have to calculate it, or accordingly we have to select and propose it. Clear? Okay, everyone. Hope the concept is clear. A little bit, I guess. Okay. Thank you.